And this was something that we were quite happy with. And frankly, it was sort of surprising to our biology friends because I think they liked us and they believed us sort of, but they sort of didn't, right? I mean, it's a bit of a stretch to have your code run on a vehicle like that and trigger sampling decisions. So there's a certain degree of skepticism about what would come back. I think they would have been happy if 2 of the samples were hard. So that's our first data set, by the way. We have better data sets than this and longer data sets than this. So that was number 1. So I just showed it to you because it's number 1. So it's one that I'm really proud of. So this was particularly nice for us because we're able to close kind of an autonomy loop, right? And so I said earlier in the talk that I'd like people to be able to, non-roboticists to be able to command these vehicles at some higher level of abstraction. So at some level, I'd like a microbiologist to be able to say, go bring me that microbe, not go sample at location XYZ, right? There's a big difference between using a robot that way than saying, go sample at XYZ, right? And so this is a very small foray into giving people a slightly higher level of abstraction at which they can use the vehicle, right? I mean, there's 100 different things you can do to make vehicles more accessible to scientists, and that's obviously not the only user base, but it's sort of one example, right? And so, what I found by doing this is, if I sort of walked up to marine biologists and say, hey, I can navigate better in ocean currents, that's not particularly clear to them what to do with it. But if I can say to them that here's some code that if you layer on top of your mission that you've laid out, it'll trigger these good sampling decisions for you. That's a much more meaningful thing for many people because they're out there to actually take water samples. They're not intrinsically out there to make robots navigate better, right? So it's an interesting kind of maybe it's very obvious in retrospect. So we've tried to work on problems that span these many areas in marine robotics. Some are fundamental to roboticists, we want to make better robots, but we're also interested in building robots that others will use, right? Will give people things like hooks with which they can actually do things. So I'm sorry I went a little long. I'd just like to thank all my students. And so I have students who work on a variety of things. These are the students over the last 5 years, students and postdocs who worked on water-related things in my lab. So I'd like to thank all of them. And I'd like to thank my sponsors at NSF and ONR and NOAA. And I'll stop here. Thank you.
That was absolutely wonderful. Do we have questions? Sure.
You mentioned about adaptive sampling, you are doing Gaussian processing online, right? But with the scale of this field, like how many samples are you running? Is it like, does it take long?
No, it doesn't, because so we grid the ocean incredibly sparsely. So the grid is in fact for the updates I showed you for the adaptive sampling, they're like 10 kilometer by 10 kilometer grid. So there's only one sample for every 10 by 10 square, and we're looking at 100 by 100 square overall for our simulations.
So is this sample at the center of the?
It is at the center, and there's actually some trickery about how you compute the sample from data within the grid. So we do some weighted averaging. So in fact, there's a layer under the GP, which I didn't talk about here, but it's a very small GP. Yeah.
But the sampling decisions in the last part of the talk, you had this IID assumption, and you had a series of K secretary problems. But earlier than that, you talked about estimating fields of these parameters that you're using for your model. So is there scope to remove the IID assumption?
Yeah, so that's a good question. So first of all, the distribution of alga in the ocean is not IID. If you're at location X and it's really hot for Pseudonychia, then epsilon away from X, ED is going to be really hot for Pseudonychia, right? So it's about as non-IID as you can imagine, right? So let me answer this in 2 parts. So what causes our beautiful secretary algorithm not to take all the water samples at the first hotspot? Well, it's because there's this enforced split between, so you take the n things you could do and divide them into k windows. So if you used up your one sample in the k window, then you wait till the next window comes. That's sort of an artificial constraint, just part of the algorithm. And there's been some work on trying to relax that. It may, in fact, there may be better techniques. Right? And one of those techniques may involve building a map, right? Which we don't do right now. So the other thing we don't do right now is, you'll notice we don't revisit locations. So I modeled the sampling problem as a problem where the trajectory was chosen in advance, and you sampled along the way. So it's completely decoupling the water sampling problem from the field estimation problem. So we have some ongoing work to try and couple those. And I suspect we'll have better results when we couple those. But I don't have any principle to say about how to couple them. I mean, I have some thoughts on how to do it in a Fuji way, but we haven't really done it in a way that we understand well.
So the duration of K, these K segments that you do, is it determined by the mission length?
No, it's determined by how many syringes you have. So K is 10 because we have 10 syringes.
No, but what is the, I mean, there's a temporal component to.
Yeah, there is. So each draw of the syringe takes a certain number of seconds. We're going to go for 4.5 hours. You divide 4.5 by that number of hours. That gives you 45,000. K is 10, so it's every 450. Yeah, and those are purely artifacts of our setup, so they'll change from vehicle.
Very nice talk. So you're modeling the conditional distribution of your biological variables on your physical variables. So if instead it was feasible to model the joint distribution, could you possibly do much better than this slightly flow down?
Yeah, you probably can. You probably can. So we don't. So there's some things we've been doing that we are not entirely sure about in this. We looked at 10 years of data, and we assumed that these models are stationary across all those data sets we have. I think if we built a joint distribution, we may figure out in some cases where that assumption was flawed, and we can do better. Right now, we sort of model this as an input-output relationship, and we sort of hide the fact that things may have changed in the ocean over these many surveys. So I think there'll be distinct gains if you model this as a larger joint distribution problem. There are also some latent variables that we neither measure nor understand, and so if you do a joint distribution and explicitly model some of the latent variables, you might do a whole lot better as well. So there's been some work in our group trying to have some of these things, trying to think through some of these things. We don't have a good handle on how to do that operationally. But yeah, it's good fun. I mean, in the end, we want to solve the joint modeling problem, the full SLAM problem, with this sampling decision problem in the full joint setting. That's the complete thing, right? What I showed really are just slices through that. Great.
So there's a lot of cool things. And the K-sector problem, right? There are a lot of things in your control, including how you compute some of the spectrals that you want to use.
Yeah.
But the thing I'll ask you about is in that longitudinal study, my guess is that the nature of the measuring devices has drifted on
Yeah.
as they've been improved. And I presume they try to normalize that out, but does that cause a problem?
It does. It actually causes a distinct problem, particularly for measuring for two of the instruments. So, temperature sensors haven't gotten a lot better in 10 years, but your backscatter instrument has gotten tremendously better. And so, in fact, those instruments are, so we've done some normalization for backscatter. Well, no, actually, we didn't do normalization for backscatter. We deleted particles below a certain size that were not reachable by the older backscatter experiment from the newer data sets, and actually looked at only the coarser measurements. So it's not strictly normalization, but we sort of tried to equalize across those. The other piece of it is a little bit tricky. They are calibrated to different standards as they've gone out. So the fluorescence measurements were calibrated to different standards, and some of those standards had been lost. So we tried to separately recover the calibration parameters to normalize, which was moderately successful, and also something we sort of made up, right? So we're not sure whether we did the right thing there, but that's how we addressed these two instruments. We didn't touch any of the other instruments. We just used the data as though it had not drifted in time. That's a good.
Maybe I'll ask one last question. So it's amazing how little actuation authority these drifters have. They're
Yeah.
really just carried along by the current.
Yeah.
So I'm curious how, if you've looked at all at changing your waypoint as the current is moving through the environment. So
Yeah.
optimizing for that.
Yeah. So I didn't talk about that at all, but we have a whole